Hey, what's up, guys? Yeah, recently I'm studying some complexity theory, and I think it's interesting. So there are many complexity class. So I want to make my own short notes, my video list discussing all the complexity theory results that I learned and I combine into my own video list. Previous there are there are already some of them. So, but in this video that I want to mainly prove some many basic complexity classes. So I will discuss PMP and PSPACE and also XP. Okay, and prove the very standard inclusive inclusion results. Okay. So idea is that let me just quickly say, right? So P is which is a decision, it's a set of the decision language. So basically, okay. So the decision language is basically the subset of 0, 1 bit string, which that some of them should be true, some of them is not. Okay. So P. Sorry. So okay. So I should say the decision language is that given a 0, 1 0, 1 bit strings and you choose a subset of it. And if X belongs to L, that means that X is yeah. So X belongs to L means that just this, yeah, just this notation. Okay. Okay, and usually so all these complexity classes only define on the decision, only on the decision problem. Basically, the output at most zero, basically is 1 or 0 or yes or no. Okay, so P is the decision, the set of decision language L, such that there is a there is a deterministic Turing machine. So you can view a deterministic Turing machine just a basic standard definition of Turing machine. Basically, there's infinite tapes. There's a tapes which is there's a tape. Sorry, there's a tape with infinite cell. Okay, and then there is a machine here, and then this machine have finite number of states, and then this pointer, right, can go to left or right and change the states and write something. Okay, so there's a deterministic Turing machine M, such that M decides L in polynomial n time. Okay, where n is, so this n is the length of the length of the input. Okay, so another way to write more rigorously is that for every x belongs to L, there this is a P, right? So P, so X, so L belongs to P if and only if for every X belongs to L, there is a deterministic Turing machine such that n accept. So such M of X output 1 in poly n time, and if X do not belongs to L, then the M, so same thing, right? So this is the center machine, right? So given L, for every, if X belongs to L, then Turing machine should output 1 in the point in time, and if X do not belongs to L, then the N should output 0 in polynomial time. Okay, so basically you can just determine this, you can solve this problem in the polynomial time. Okay, so there are famous example like sorting. Sorting is not a decision language, so you need to change it a little bit. Okay, and or like somebody will give you a large integer and you choose another m and ask whether m divides n. Okay, so this is whether n is divisible by m or m divides n. This is basically just a division. Okay, and NP is the non-deterministic polynomial time, which is usually definition looks like for every x belongs to L. There is a y which with the length which is this y is at most the length is at most with x the poly length. So basically x is let's say this is so y should be poly at most length of poly x, such that and then there is a Turing machine M, which is a deterministic Turing machine M, such that M accept so basically M x y output 1. Okay, so this y is called certificate. Okay, and this M is called a verifier. Okay, so this is like a standard. This is like the standard approach. Okay. Okay, and this is just you also need to write another sentence made basically for every x do not belongs to L. Right. Then for all the y with that length, right? Or y with this poly x length. Actually, I can write this. Okay, that mxy output 0. Okay. Okay, so this means that if x do not belong to this language, then for every length with poly n x, this m of xy will output 0. Okay, so the famous example is I think everyone knows, right? A set. Okay, reset or the circuit set. And then there are a lot of problems which is called NP complete. There are a lot of it. I make my own video that use the idea called reduction to step by step connect each NP complete problem. So I will post the link below that you can check. There are a lot of them. Basically, some of them is like a vertex cover graph, some graph problems, also TSP, Hamiltonian graph, subset sum. In integer linear programming, there are a lot of NP complete problems. Okay, and obviously that all these problem is the NP complete problem, and obviously they all belong to NP because for example, right there, because this problem as query you got something, right? So if you got it, then you can just find answer and you can check this M is simply the Turing machine and just check the answer, and then you can check that is okay. I forgot to write important things is that and need to run in poly time. Okay, so basically for a set, sorry, the circuit set is a formula that you have formula like this. Okay, and basically composable with n or not, and if you ask whether this set this quantifier is satisfiable. If it's satisfiable, that somebody just give you a number, give you the assignment, whether maybe x1 is true, x1 x2 is false, then your deterministic algorithm just simply check that whether this is true or false, right? So this M just need to run in polynomial time. Okay. Yeah, this is the definition. Okay. Also, let me define another, which is a PSPACE. Okay. So PSPACE. Okay, simply speaking, let's just write down. So let's write down this definition. So PSPACE are decision problems that are solvable in a polynomial space. Okay, so idea is that let's say your input is n, and there is a deterministic Turing machine which decides L. So there, simply speaking, is that there is a decision Turing machine M decides L in only using polynomial space. Okay. So fact, which is very trivial, is that the P is a subset of P space. Okay, so the reason is very simple. The reason is that the polytime algorithm, right? Because the polytime algorithm, you just imagine that you have a Turing machine with this tape, and the tape only take the polynomial steps, right? So poly and algorithm, I say poly and time algorithm only only uses Polygon space. This is trivial, right? Because you only spend like Polygon time, so you can at most use the Polygon state Polygon spaces, which is the Polygon cells. Okay, and also trivial is that P is a subset of NP, which you can easily prove. By definition, you just run your deterministic determination to solve P, right? So we don't care about the verifier. Okay, so fact that we are gonna to prove is that NP is a subset of P space. Okay, the proof. A proof is very simple. Okay, so we all know that the 3 set is NP complete. Okay, so the only thing we need to prove is that 3 set is a P space. Okay. This is simple, right? Because so 3 sets means that somebody give you a formula, not formula, but the conjunction 3 normal form. But let's write it as a phi, and then let's say we have a variable x1, x2 up to xn. Okay. And we want to run given a P space algorithm that this P space, it only takes the polynomial space. Okay, so this algorithm is very simple, right? Just one sentence. So basically try all possibilities. Okay, so the problem is that there are let's say each x1, x2, and xn can at most be 0 or 1. So total we have 2 to n choices. Okay, so we only need n cells, right? Because each cells or each bit we only need n bit. Each bit can at most can run 0 or 1. Okay. Okay, so it's very simple that I can create n bit, and I may create another bit, which is for a record, and I just run every 2 to n choice. So for each choice, I only need the poly n times to decide whether it's 0 or 1. If it's 0, then I just write 0. So once I get all 1, once I get 1, 1, once I get one assignment such that the result is 1, then I just output 1, because this means that this phi is satisfiable. If after I try 2 to n choices, if there's no any assignment such that which can make the results become 1, then I just output 0. Okay, then just output 0 if none of choice works. Okay, so actually this simply try all the possibilities. And how many space I use, right? I just use n plus 1 space. Okay, so 3 set is a P space. Okay, and another complexity class that I would say is that this XP. So XP is simply decision problem. There is a Turing machine. There is a deterministic Turing machine that decides the language. Let's say L belongs to XP. If only if there is a the set of DC problem, there's a Turing machine M decides L in 2 to the x time, poly x time. Okay, so this is that you can write a problem, you can solve the problem in exponential time. Okay, so there's a theorem that I previously proved in my previous proof in my video list called time hierarchy theorem. Okay, which you can use the Cantor's diagonalization techniques to prove that P is strictly less than XP. Okay. So this is, if you are interested in this proof, that you can check out my video. Basically, this is interesting proof that the idea. Let me just write down the key idea. The key idea is just the Cantor's, the famous mathematician Cantor, the diagonalization technique. Okay, this is the same as you want to prove that the real number is uncountable, or the cardinality of the real number is strictly larger than the cardinality of integer. Okay. Okay. So let me just, yeah, this is simple, right? This is very simple. So the tricky part is that we want to prove the following. Okay. Because the P space is a subset of XP. Okay. How do we prove this kind of thing? We want to say that if you have a point determinate Turing machine that you only if you have a language which you only need a polynomial space that you can solve it, and then you at most need a polynomial, you at most need exponential time. Okay, so proof is a simple idea. Let's suppose, okay, let's say you suppose come here, right? You suppose come here, you have a Turing machine, okay, and then you have some internal states. Okay, so let's say you total have different k internal states, and if X belongs to a P space, sorry, if L belongs to a P space, okay, so that means that and then you only need point n space. Okay, so that means you can only use P of n cells. Okay, and let's say for each, let's imagine that for each cells you only have two choices. Okay, so that means you get 2 to the Pn different choices. This is all the possible string that you can write, and your internal state is k. Okay. Okay, so this means that this means what? Okay, so this means that this k times 2 to the Pn is all a bit string. This is all a bit string, all the possible string that all the possible strings that you can write. Okay, and if you times Pn, P of n, then this number will be the total configuration space. This is all the different configuration, because your Turing machine has internal k states, and you have you can at most use 2 to the cell, right? 2 to the Pn. Okay, and at most of Pn operations. Okay, so your k times okay, so your Pn is the position of the this is the position of the pointer, or position of the pointer, or the position of the head. Okay, so this is total configuration. Okay, so let's call it Tn. Okay, so since it's P space, right? So your Turing machine must terminate, must halt in Tn time. By definition, right? Because your language is P space, so your Turing machine must halt in Tn time. Okay, where Tn is what? Tn is an exponential time, right? So Tn can be written as 2 to the Qn for some polycube, for some polynomial cube. Okay, so which is a proof P space is a subset of XP. Okay, before we finish, I want to describe a thing called TQBF. So TQBF is a quantifier question. Okay, so the idea is that somebody give you a formula, but you add some quantifier. Okay, so let me just, so usually in a stat problem is that somebody give you a formula as x1 xn, and you want to ask whether the following is true. You want to ask there is a x1 x2 xn phi. Okay, so this sentence means that I want to ask whether you can find x1 x2 x up to xn such that this phi of x is true. Okay, and the general TQBF is that you can modify this existence to be for all. Okay, so for example, you can ask, there is x1 for all x2, there is x3 for all, maybe for all xn, phi of x1 up to xn. So this is much more difficult, right? Because somehow that you can replace some of the verifier to be for all. Okay, so there's a fact that let me just give you the proof for TQBF is a subset, is a language, it's a piece-based language. Okay, actually more difficult is that I will not prove it in this video, which is Starmer, I think it's 1973, that one can prove that TQBF is a piece-based complete. Okay, let me just prove that TQBF is a piece-based. This is what I want to say in this video. Okay, this is simple. The reason is that I think this is the same, right? You understand what the detail. Okay, because previously, if I want to prove that the three circuit set is in a piece space, then I just iterate all the possible examples, and I only need one extra memory to record results. Okay, but now I have this, right? So I can just what? Let's say somebody ask you this, and then you want to say that, oh, maybe you want to design a algorithm that only uses a polynomial space. Then the simple way to do this is what? Just do the same thing, right? Iterate all the examples, but you totally get 2 to n choices, right? So you can make a table to record all the choices. Okay. So you can use extra. You can use extra. So idea is that I first choose everything. I choose one assignment and put in compute, and I choose another and put in compute, and I choose another and put in compute. So I just use an extra n bit to record every, so to record 2 to n results. And then finally I just check the formula. Okay, so yeah, this is a proof. Okay, so one example is that let's say somebody asks you for all x1 there is a x2 such that phi x1 x2 is true or not. This is simple. I just choose x1 to be 0, and I choose x2 to be 1 0, and I choose 0 1 1 0 1 1, and I just compute 4 results, and I check whether this formula is correct. Okay, so if this formula is correct, means that for every x1 there is an x2 such that this is true, right? So I want to check that whether 0, whenever I choose x0 1, there's always another x2 such that this is true. Okay, so you need to check this. For example, 0 0 2 0 1 false, 1 0 true, 1 1 false. This is one possible answer, and you see that I only need to compute 4 times. So I only need to compute 2 to n time, and I just check whether the formula is true or not. Because obviously TQBF is in the piece space, but it's not obviously that the TQBF is a piece space complete. Okay, and one can actually start from here and prove that the TQBF is the same as the two-gamer. It's the best. It's the largest complexity that for two-gamer playing the game with the perfect information. So two-gamer or winning strategy with perfect information. Okay, this is all I want to say for this elementary complexity class. I think this is enough. So basically, the rest is just some NP reduction. But once you understand this idea that you already have some feeling, and the next time I may talk about the PPP and the PP and other complexity class, which you can encode it with the random bits, or basically you can encode it with the probability that you got something which is really interesting. Okay, see you guys next videos.